In this video, we're going to discuss the free energy of formation. So we know that we can calculate the free energy change for a process using the Gibbs free energy equation. However, we often need another method for calculating delta G. We can calculate delta G, or the free energy changes, using something called the standard free energies of formation, and that's what we want to discuss in this video. So this allows us to calculate delta G under standard conditions, only under standard conditions, for any chemical reaction. So what is the standard free energy of formation? Well, standard free energy of formation is abbreviated as delta G standard with a little f for formation of a substance is the free energy change for the formation of 1 mole of a substance in its standard state from its most stable form of its constituent elements in their standard states. Now that's a mouthful, so let's look at an example to help us illustrate that. Let's look at the equation showing the free energy of formation for methane, CH4. Okay? It would look something like this. And what we have here, we're showing the formation of 1 mole of a substance. So here we have 1 mole of methane. We're forming that, so that's our product. From in its standard state, well, methane is a gas in its standard state, from the most stable form of its constituent elements in their standard state. So we're showing the formation of 1 mole of methane from its constituent elements, so carbon and hydrogen in their most standard states. So here we have carbon solid, this would be graphite, and 2 moles of hydrogen gas. The most standard form of hydrogen is the diatomic H2. And again, we have to balance this, so we have to have 2 of these. But always we have 1 mole of our product. We can have 2 or 3 moles of reactants, but we must always have 1 mole of product. So the values for delta G of formation, we don't have to calculate those. Those are given. We have tables of these delta G of formations, and you have a large table in the appendix of your textbook. So here, this is just a small sample. We can see that the delta G of formation for methane is negative 50.8 kilojoules per mole. So we could tell that if you were to form 1 mole of methane from pure carbon solid and pure hydrogen gas, if you were to form 1 mole of methane, it would release 50.8 kilojoules of free energy. So that's the amount of free energy in this case that's released, because we have a negative sign, for the formation of 1 mole of methane. Another thing that's important about free energy of formation is that any elements in their standard state are assigned a value of 0 kilojoules per mole. So they're set at 0, anything in its elemental state. So elemental states, again, we mentioned hydrogen. The elemental form of hydrogen is H2, oxygen's O2. Most of the gases are diatomic, as you can see here. The noble gases are, of course, just helium, neon, krypton, etc. And metals like iron, aluminum are just the elemental form that you would find on the periodic table. So anything, any element or substance in its elemental form is assigned a delta G of formation of 0. So here, let's look back at our equation for the formation of methane. The delta G of formation for carbon would be assigned 0. For hydrogen would be assigned 0. And then the methane we got off our table is negative 50.8 kilojoules per mole. So let me have you practice writing a couple of these equations showing the free energy of formation for each of the following molecules. See if you can write an equation showing the delta G of formation for carbon dioxide, nitrogen dioxide, and acetic acid. Pause the video for a second, give it a try. Okay. So for carbon dioxide, we want to form 1 mole of CO2, and it's going to be in a gas form, from carbon and oxygen. Those are its elements, and we have to have those in their elemental form. For NO2, this one's a little trickier. We have to form 1 mole of NO2. Nitrogen is not N, but N2, diatomic. Oxygen is O2. So to get our equation to balance, we have to have half a mole here, because again, delta G of formation is for 1 mole of the product. For acetic acid, again, for 1 mole of acetic acid, we have to have 2 carbon atoms, 2 hydrogen molecules, 1 oxygen molecule in order to form 1 mole of acetic acid in the liquid form. So these would be the equations for delta G of formation for each of these substances. Now we can get the values for delta G of formation for each of these from our table or the appendix in your textbook, and then we can write each of these showing their delta G formation. So for example, for carbon dioxide, if we were to form carbon dioxide, 1 mole of CO2 in the gas form from graphite and oxygen, it would release 394.4 kilojoules per mole. Now those are great, but why do we need to know the delta G of formation? Why is it important to understand the delta G of formation for any compound? Well, the use of this, the utility for delta G formation, is that it allows us to calculate the standard free energy change, delta G of standard, for any chemical reaction. So using these delta G formations for these individual molecules, we can calculate the delta G standard for any chemical reaction. So this gives us another way to calculate delta G, as we mentioned before, if we don't have information about enthalpy and entropy. The formula that we would use to calculate delta G using the free energies of formation is this. The change in free energy under standard conditions for any reaction is equal to the delta G of formation for the products minus the delta G of formation for the reactants. So if we have a reaction that looks like this, our equation would expand to include this. We'd have the delta G standard is equal to the sum of the delta G's of formation of the products times however many moles of the products we have minus the delta G of formation of our reactants times however many moles of each we had. So let's try a problem to help us illustrate this. Using the table values, and I'll put that up in just a second. Again, you can use the appendix from your textbook. Calculate the standard free energy change at 25 degrees Celsius for this chemical reaction. Okay? And then tell us whether this reaction is spontaneous or non-spontaneous under standard conditions. So pause the video and give it a try. Okay, so using our formula and the free energies of formation, we should be able to calculate the standard free energy change for this reaction. We would calculate the free energy change under standard conditions by taking our products, 2 moles of iron, the delta G of formation for iron, plus 3 moles times the delta G of formation of carbon dioxide, minus 1 mole times the delta G of formation of iron 3 oxide, plus 3 moles times the delta G of formation for carbon monoxide. And again, the 2's and 3's come from our stoichiometric coefficients. So if we plug in the values from our table, we get this. Now iron, that's the elemental form of iron. So the delta G of formation for anything in its elemental form is 0. Plug in the rest of the values, we should be able to solve. And we get a change in free energy for this reaction under standard conditions of negative 29.4 kilojoules. That means that this reaction under standard conditions is spontaneous. So be sure you're familiar with the concept of standard free energy of formation and be able to calculate the free energy change for a reaction using the standard free energies of formation.